The lecture for today is an introduction to logistic regression. An introduction. So you're not going to do the detailed work. It's just an introduction, a kind of a bit of the theory, and it's the basic. You will do this properly next time. Is this your first semester or second? First, isn't it?
First semester.
Exactly. So you would do the proper one. But this is just an introduction. That I was told that I should give you this warm introduction so that next time when you encounter the real deal, you are not so much overwhelmed. So I want to welcome you to the Valley of the Shadows of Statistics for Business. And like I said, it's just an introduction. Okay? You should be able to distinguish between a linear regression and a logistic regression. You should know that. You should know how to distinguish between the two. You should be able to compute a logistic regression model. Today we'll look at the model, then you can learn the estimation of the model next time. You should be able to build and interpret the results of the logistic regression. That is a practical application. I'll give you the data, but I will not go through the details today. Interpreting the output of a logistic regression is very, very important. Okay. And then how to ensure that the model is performing well using different kinds of hyperparameter tunings and all of that. But like I said, those ones are all next time. So let me take you back to something you guys already know, probably, hopefully you know. In a supervised learning, okay, so the whole concept of machine learning, okay, you got supervised and unsupervised. Remember that the whole idea of machine learning itself is a microcosm of artificial intelligence. And there are other things. So sometimes business analytics bring in more things outside just artificial intelligence. So business analytics is broader than AI, okay? And one of it is this AI, and AI is subcategorized into multiple things. There are several things: computer vision, deep learning, machine learning, you know, text analytics, and several things are in there. Within the area of machine learning, that's where you have the principles of supervised and unsupervised learning. And I know you've learned them already. Under supervised learning, there are two major applications, or there are two major methodologies in there. The first is the classification, and the second is the regression. Now, the classification uses classes or categories or groups, okay? And the regression uses real numbers, actual numbers. So one of the assumptions of regression is that you must have real numbers. So sometimes even when you have categories, you got to code them and make them real numbers. Also, when you're doing basic regression, simple regression, basic regression, the goal here is for the dependent variable. As you have seen, the dependent variable is what's supposed to be the real numbers. Okay. But the moment we enter into a situation where the dependent variable is not a continuous variable, but it's a string variable, it's a dummy, then it changes. Then we are more or less within the areas of categories. So under regression, you have things like linear regression, decision trees, you know, support vector machines, and all of that. Under classification, you have logistic, naive, and also a portion of support vector machine can also be classified. Under the linear regression, you can have linear regression, non-linear regression like polynomial quadratics, all of them are there. And also, you can also have support vector machine, random forest, this is it. Now, what you guys are seeing here is not a continuation. It's just part of this, but I didn't want it to be small. That's why I brought it to the fire. So classification, you have logistic, naive, support vector machine, decision tree, random forest, all of them. The logistic regression, you will note that it uses something known as the sigmoid function or the logistic function. And it looks more at the presence or the absence of something for the dependent variable. Okay, let's get into a bit of details. Where can you apply logistic regression? Where can you apply it? Well, we've already said that linear regression uses metric numbers for the dependent variable. The dependent variable is the left-hand side. That is the one being influenced, or that is the one whose behavior is being explained by multiple predictors, multiple regressors, multiple independent variables. Now, in the case of a logistic regression, the dependent variable is no longer metric. It's no longer numerical, but it becomes non-metric, categorical. Sometimes it is discrete or nominal. Okay, discrete or nominal. So there could be multiple, coding for the dependent variable, or it could be discrete, single values, that is 0 or 1. And therefore, that makes it binary or dichotomous dependent variable. So when the dependent variable is dichotomous, that is when the logistic regression comes in. But what do we really mean by all of this? Well, let's take a couple of examples. If you have a situation of loan, so let's say that you want to give a loan, okay, and somebody applies for a loan, the bank will have to approve or reject the loan. The probability of approving or rejecting the loan is a logistically determined function. It carries with it a sigmoid function. It carries with it a logistic function. Because you can't say that I will approve, because there are two options that will come. By going to the exam room, the possibility of failing and passing are all there. So the outcomes are binary. Sometimes they are even multi-binary, multinomial. In a medical diagnosis, you want to check if a tumor is cancerous or is not cancerous. If the tumor is cancerous, dangerous, or malignant, okay, or it's not cancerous, it's not, it's benign, it's not harmful, that is a principle of a logistic behavior. But how do you know? What is the probability? What is the likelihood that that is going to be the case? Now, in another example of buy or not to buy a product, okay, should I buy or I shouldn't buy a particular product? This is also an example of a logistic behavior, okay, that you have to apply. So all of these, you can get your thesis, your research topic, on any of these, okay, and you can get data and use it to make your point. Look, at the end of the day, making the hypothesis and using your data and coming out with it, that's the whole thesis that you will ever do. Of course, what I'm teaching you is a classwork, but this is the same thing you can use for your thesis. When you're looking for a dissertation topic, these are some of the areas you can pick some things from. Fraud detection is a typical example. If a transaction is fraudulent or is not fraudulent, suppose somebody comes to take some money, or somebody applies for some money, the bank are supposed to put some mechanisms in place to detect whether this is a fraudulent transaction or not. In such a case, you have a binary outcome. A web page can be categorized as to whether, suppose somebody sends you an email, some of the emails immediately will go into your spam. How did the email know? Because the email systems has been designed to be able to fish out those that are phishing and those that are adult or those that are malicious, and things like that. So sometimes there could be an advert, and an advert, you want to know whether the advert is a malicious advert or not. If you have a nothing will just send it to the appropriate place. How did they detect that? Okay, this is an algorithm related to a binary behavior. Let's take a practical example of recent. Would the people of Ghana vote for the MPP if there are elections next time? What would you say? I need an answer from one of you. Will the people of Ghana vote for the MPP in the next 4 years election, or they will maintain this one? What do you say? You don't know. The chances are either positive or negative. Okay, nobody can tell. Okay, and that is a typical example of what we mean by a logistic behavior. If you have an online retailer like Amazon, Alibaba, you need to predict. You need to predict which of the product a particular customer is most likely to buy. If a person buys a mobile phone, the likelihood of the person buying a charger is high. If a person buys tomatoes, the likelihood of the person buying other vegetables is high. Okay, so that probability. So you receive a data set with past visitors to the website, and then you also monitor their purchases from the online retailer. And based on that, you'll be able to know exactly what the person is going to buy next. And by tracking the record, you'll be able to make a prediction. Now, let's go back to remind ourselves of what a linear regression is. A linear regression is like this. You have a dependent variable on the left-hand side. This is a metric dependent variable. You have multiple independent variables. Some of them are dummies, some of them are numerical. You have an error term, let's say A. I can rewrite it like that to make it generalized, okay, as you know it, which will have a constant, it will have an error term as always. I can also combine the generalization into this format. So the dependent variable is metric, it's continuous. Okay. And a typical example of such is wage. So wage will be the dependent variable. There will be multiple independent variables that are affecting the wage, like salary, that are affecting the wage, like experience of the person, the position of the person, the education of the person, and several other things. You can also have quantity demanded as a dependent variable, which is being influenced by the price, the complement price, the income, the population, and things like that. You can have the blood pressure of a person as a dependent variable. The blood pressure here will be affected by the weight of the person, by the height of the person, by the exercise level, by the diet of the person, by other diseases of the person. So these are all metric, dependent variables. But what if the dependent variable is not metric? What if it's dichotomous? What if it's binary? Let's take a typical example. Okay. So here you have factors that are influencing the presence or the absence of a disease, say tumor. So you have the disease here, and the disease, whether I've not indicated a particular disease, but let's say it's cancer, okay, or let's say it's a tumor. You don't know whether it's cancerous or not. No. And this tumor, you believe that whether or not the person will have the disease, the presence or the absence of the disease is influenced by the age of the person. It's also influenced by the gender of the person. And it's also influenced by the smoking status of the person. So these are the factors that will affect the presence or the absence. So we are not interested in whether the disease is high or is low. No. High or low makes it continuous. But we are looking at 0 or 1, presence or absence. Okay. And this, to detect whether the disease is absent, which is 0, not diseased, or, so this is not disease. Okay, this first one. This first one is not diseased, okay, which is symbolized by this. And then the possibility of it being diseased, okay, the person having that disease is also given as 1 here. The probability of the occurrence of the disease or the occurrence or the presence or the absence of the disease. The probability of the presence of the disease, the probability of the absence of the disease is binary. And in this case, the dependent variable becomes 0 or 1. And if it is 0, you know that there is an absence of disease. So to what extent does age influence the absence of the disease? To what extent does gender influence the absence? To what extent does smoking? If it is present too, to what extent does age influence the presence? To what extent does smoking status influence the presence? So we can estimate the probability of that occurrence. And that is what requires a different function, a different model to look at. We'll take another example. You will appreciate this example. So I have data set here. I have a data set of diseases. Remember, the data ends in the middle here, and then it continues here. So I have diseases here, and the first person, I have some individuals. The first person is diseased, as you can see. The second person is not diseased. The third person is diseased. The fourth is diseased. So you are able to know, so you have this data set, and then you've also collected their ages of each one of these people. So the first person is 43, and that 43rd person was diseased. But the guy who is not diseased was just young, 18. Okay. The one who is diseased was 22, 25, they are all diseased. And when you check it, the gender is also there. You want to know whether gender is playing any role at all in affecting whether the person is diseased or not diseased. And then the smoking status. The first person is a smoker. So remember, he's older, he's a male, and he's a smoker as well. So you are able to have these characteristic behavior. We can examine the influence of these independent variables, each one of them, on the tumor, the presence or the absence of a tumor. Now, if there is any influence at all, okay, then we can now use that to predict how likely it is for the person to have a disease, given his age, given his gender, given his smoking status. You can do that. Now look at the smoking status. You will also note that the smoking status is a dummy variable, 0 or 1, 0 or 1, 0 or 1. The same way the disease is also a dummy variable. I can say that diseased is 1, not diseased is 0. Okay. Now, why don't we use a regression, linear regression model? Why can't we use that and be free? Well, you're going to see that very soon. That's the essence. Suppose we scatter plot the data. And by the way, I have the data here. Let me see if I can. Oops. Sorry, my computer is frozen. Sort of. It's frozen. All right. So I'm going to go. Oh, what is happening? I'm trying to resume the. All right. So when you look at this data set, okay, this is a data set I told you about. Come on. So this is a data set. And I think I made an error. This side, no, I think it's the same thing. So let's go here. This is a data set. And what I decided to do was, this was the original data set, was to code this one. And you can easily do that using the find and replace in Excel. Okay. And then you can code. And I decided to code this very one. Actually, I could have coded this one. Okay. So let me just show you exactly what I mean by I could have coded. You copy the same thing from here. I'm just copying the whole thing. I'm taking it to this section here. Let me just drop it here. And I will just use find and replace to code the disease. So go to home. This is find and replace. Okay. And you just have to type the word diseased. I'm replacing diseased with 1. Of course, the heading will also change, but no problem. We'll come back to that. And I'm going to look on the left side. Once you click replace all the diseased have become 1. Okay, so that is done. Now the not diseased, it is now not 1. So I'm going to replace that one too and choose replace not 1 with 0. And watch all the not 1. They are all going to be 0 on the column A. So you click that. Oh, sorry, I made it. Oh, no way. It should have been 0. I chose 1. Let's do it again. Replace not 1 with 0, and I wrote 1, 0. So now let's do that. And there you go. So you can see that all of the diseases have been coded as 1 or 0. So 1 here means, is that how this thing was? Let me be sure. Yeah. Not 1 is not diseased. 1 here means disease. Okay, good. So let's move on. So what we can do is that we can look at the relationship between age and disease. You can look at the relationship between any of them and disease, any of the independent variable. Now, how do you do that? You can just generate a quick scatter plot. So I can highlight the whole of this. Okay. Okay. Do Control A, and then you highlight everything. If it was a lot, you would have used control systems to be able to get all. And then you go to Insert. And then on the right here, you choose Scatter. And then we scatter plot this thing using that. Come on. All right. So now we have this scatter plot, and you can see here the values that have been here. Now, it would be nice to rather switch them. Okay. Switch them so that this one goes here, this one goes here. Because here it has been done horizontally. So let me do it vertically. What do I mean by vertically? What I mean is I just copy this one here, bring the age first. So I'm just going to take the age first and then bring the disease second. Okay. Now, let's get how it looks. You do insert, you do scatter, you do that. Now it looks proper the way it's supposed to be. Okay. Now you can use the axis. Okay. You can label the axis. So if you look at the numbers carefully, the y-axis, let me just go here and choose this one. Okay. This one would allow you to just input it. Y-axis is the disease. Okay. This is disease. Not diseased, but disease. Disease. And then the x-axis is the age. So you label it. And then you can remove this title, can remove this legend. And now something interesting is happening here, guys. You can see clearly, let me make it bigger. You can see clearly that all the numbers are pegged between 0 and 1 for the disease. So it doesn't matter the dependent variable, age, okay? It doesn't matter the dependent variable age. You will notice that no matter how older you are, your disease value is going to be limited, range between 0 and 1. And do you know how interesting that is? It means that when you put a regression line on it, there's going to be a problem. And I'm going to show you that very soon. Let's say that I want to put a regression line. Still go to chart format, chart design, click on layout, and instead of what you have, just choose this layout because that will draw the regression easily for you. This layout. See this layout? There you go. Okay. So this layout that I've just done, let me remove the heading. Let me remove the legend. And now look at the layout. This line, as you can see, it goes to positive infinity if we have to stretch it. And if you stretch it downward, it will pass down here and it will go to negative infinity. This is interesting, ladies and gentlemen. It is very interesting because I'm going to use this one to make a case for what we are studying. Where are we? Oh, my PowerPoint is gone. Just a second, please. For some reason, the PowerPoint is gone. Right. So you can see that this is a data set, okay, with the disease and not diseased. Now, we decide to scatter plot the data. But what I did was to use scatter plot disease and age. That's what I did. Okay. So you can see that this one here, the one you see down here, is that x-axis is supposed to be age here. And then the y-axis is supposed to be the presence of disease or not disease. Now, guys, as you know, the possibility is that normally we know that as a person is aging, then the person's sicknesses are increasing. But you can see that this has limited. Either you only have a disease or you don't have a disease. Okay, so there is no middle line. You can't have half a disease, quarter of a disease, 0.8 of a disease. That's why you can see that all the values are either peaked at 1 or limited at 2 below. And in that case, if you run a regression model, the reason why linear regression will not work is what I'm about to show you. That's why I put here, why not just use linear regression and be free? Well, this is it's a multiple regression model that you can see above there. Okay. Because the dependent variable is between 0 and 1, as you can see here, no matter the values of age, no matter the values of the independent variable age, only 0 or 1 is going to result, as you can see here. You are either going to get 0 or 1. And so it means that, and regression doesn't require the dependent variable to only be between two numbers, OLS regression. So we decide to use regression to see the result. And you can see that if you use regression, okay, then the values are going to be between negative infinity and positive infinity. This will occur. How do you know? Because you look at this regression, if I stretch this line, it's going into negatives. This is a typical demonstration of it. Okay. So it means that, if you look at this example, it means that disease will be in the negatives, and even age will be in the negative, but we don't have negative age. So using a regression makes it doesn't fit the model. It doesn't reflect the behavior of the model, the behavior of the items being between just 0 and 1. You see, you can use a regression to run the profit of a company, which can also be a loss. Okay, the profit of the company can be positive, and then the profit of the company is positive, and the loss is negative. That is all for the company. It's all for the company. It's possible. It's possible. That is why you can use OLS regression to run and fit that model, because it's all possible. But then you can't have negative 2, negative 70. That is not possible. So because that's not possible, you can't use an OLS regression to try and do that. And that is why a linear regression will not suffice here. Now, what does a logistic regression do? Well, the goal of a logistic regression is to estimate not just the value of the variable itself, but to estimate the probability of the value, the probability of the occurrence of the variable. That's what a regression is doing, a logistic regression is doing. Now, guys, note the difference. I want to estimate a value of something, meaning that you know that that something is there. That's why you are estimating it. But I want to estimate the probability of something happening. It means that it may not happen. That is why you are trying to estimate this probability of it occurring. And it's true, a person may not have a disease. A person may not be fraudulent. A person may not be guilty. But you think he is guilty. So you got to estimate the probability of it being guilty. And whenever something may or may not happen, then its probability of it happening is what you should find, not it happening, as if it's happening. So when you look at profit, okay, the profit will happen, the loss will happen, it is happening. You know it. And so you got the values for it. And based on that, you can now, even the profit that I've used is not even the best one. Suppose you want to look at quantity demanded. Once you buy you produce your goods and you want to know the quantity, you will get data for the quantity demanded. But if this time you want to rather look at whether or not people will demand the quantity, then in this case, you cannot use regression. I mean, no less regression, linear regression. But you have to use what? You have to use a logistic regression. So the goal of the logistic regression is to look at the probability, which is also the prediction of the occurrence of a particular event. So the equation you have here, this one, the linear regression model, okay, that you have here, where you have the dependent variable being influenced by x1, which is an independent variable, x2, which is an independent variable, xk, which is an independent, okay. This cannot fit the regression behavior. So we need to do something about it. We need to transform it. How do you do the transformation? Well, we transformed it by restricting the values, because remember, in that OLS regression one that we did, the values are infinity. It can go all the way to infinity. But here, we got to restrict the value for the prediction to range between 0 and 1. How do you do that? Well, in order to ensure that the values are between 0 and 1, you got to use a sigmoid function. What is a sigmoid function? A sigmoid function is also called S function. It is a function that is not in our area, it's in a different area of mathematics, which allows you to fit something that is always between 0 and 1. Something that is between 0 and 1. Something that is happening or not happening. But I normally don't even like the word between 0 and 1 because it might make it look like, it might make it look like it can be 0.2, 0.5, point that. No. Yeah, even though that is a possibility, it is either 0 or 1. There's a difference between 0 or 1 and 0 and 1 and 0. No, 0 or 1 and 0 and 1. So 0 or 1 means you cannot be between. You gotta be 0 or 1. So it's like a male and a female. You either male or female. But when you say between 0 and 1, that can be rather gender. Probably. I don't know. But I hope you guys get what I mean. So this is a sigmoid function. Now, look at a regression, the OLS. This is the OLS. If you fit this line here, okay, this line keeps going up and keeps coming down. It doesn't fall between the upper value of 1 and the lower value of 0. So a linear regression will not suffice. But if you look at the sigmoid function, no matter what the values of the independent variables are, look at it. The independent variables can be negative. It's okay. It doesn't matter. But it doesn't matter what the independent variable, the S function, that's why it's called sigma. The S lookalike function will fit it between 0 and 1. So between minus and plus infinity of the independent variables, only 0 and 1 of the dependent variable can resolve. And that is exactly what we want. we want it to be between 0 and 1. This is what we call the segment function. This is what we call the logistic function. But it's not yet a logistic regression. It is a logistic function. It's not yet a logistic regression. Because this function can be used in other areas of life that are not logistic regression related. It's a function that is already there and used in several quantum mechanics, radiography, and several other things. Now, this is a logistic function. This is a segment function. Look at it here. It is f into bracket z equal to 1 over 1 plus the exponent to, the natural log raised to the power negative z. The only thing that we got to know here is the z. Everything here, we know it already. What is the z? The z is the input value that more or less sigmoidize the function, the z value. So we've got to know the z value. In our regression model, the linear regression is this. Okay. This is a linear regression. This is the regression that ideally will be the linear regression. So instead of this linear regression, we dump this whole, because this is our input, we dump this whole linear regression, which is an independent variable, into the z section. So that is become our z. That is the input value. We move this one, okay, and then put it into the z function. And so we have this function as the logistic function or the logistic regression model. Now, the way this thing looks like very clearly, it is very strange to even interpret it. But what does this mean? Let's try to get it. Because remember that this whole thing on the right-hand side is the y, as you can see here. So y is the whole of this. So, but the y itself is split into 2, isn't it? Y can be 0 or y can be 1. So it means that all of these things can be 0 or all of these things can be 1. Now, if x1 is 0, does that make all of these things 0? No. If beta 1 is 0, does that make all of these things 0? No. Okay. So the y depends on multiple things here. So this whole thing, if I have changed this whole thing on the bottom side, it means that I have to change this whole thing because that z here is representing this whole thing. But that z is the left-hand side. And the left-hand side is this y. So it's rather the y that I'll have to replace it here. But this y itself is split into 0 or 1. So I need to be clear which y I'm defining. So I'm about to define y properly. The probability that the dependent variable y is 1, and I'm just taking 1. You can do for 0 too. The probability that the dependent variable y is 1 is given by the above equation. Okay, but this is given by the following independent variables. Let me just show you here, because that is the full logistic regression model. So watch it. The probability that y is 1, that is the probability that a particular person is diseased, given that person's age, given that person's gender, or sex, or given that person's smoking status or anything, given all of the x's, the probability that the person is diseased is given by this whole thing on the right-hand side, this whole function. So when you bring it into our specific model, suppose we want to model our specific one, specifically the data we had, we say that the probability that a person is diseased or a person is having a certain disease is given by 1 over 1 plus the natural log of age, male, or in this case, the gender status, which happens to be dummy as well, okay? And then smoking. Now, remember that the independent variables, some of them can be numbers, numerical, like age. Age is numerical. Some of them can be categorical, like, sex type. And some of them can be, categorical or dummy, like smoking state. So this is a formulation of this model. How do you estimate this whole logistic regression model? So when you are writing the formulation of the model, this is how it's got to be. Okay, this is the way you formulate a logistic regression model. Well, how do you do that? How do you estimate? But not even just estimation alone, guys. How do you even interpret the results? But at least you know the model today. How do you estimate? Well, we have to solve this logistic regression model. And solving it simply means that we need to find beta 1 or B1, B2, B3, and all the other beta coefficients. Because those are the ones that will fit the model. The method we use is known as the maximum likelihood method, or the maximum likelihood estimation. This is like the OLS, the ordinary least squares. And what this one does is to estimate the beta parameters of the model, the B1, the B2, the B3. We're not going to do this today. We are going to take our time and use that data we showed you earlier. And then we will look at that next time. Okay. Or probably we'll look at that next semester. But this is just an introduction to what is known as the logistic regression. Okay. And yeah. Somebody has started interrupting us. Emmanuel Ito. Okay. So what we do now is that next time, what I'm going to do is I'm going to take the practical data set, and then I will demonstrate how to interpret the logistic regression model. I will use Python or I will use R, but I think I'm going to use Python more. I'll use Python to demonstrate to you, but more importantly, to interpret the results to you. We shall talk a lot about odds and odds ratio and log likelihood ratios and several other things. We'll use this thing to bring home the point of what we are saying. Ladies and gentlemen, that brings us to the end of the entire caboodle for today.